So we're going to finish section 2.2 and possibly section 2.3 today. We've been building up to the matrix representation of linear systems. And so let me just remind you of what we have so far under our belt. So the learning objectives for today are, first of all, that you become completely comfortable with the matrix representation of a linear system, and that you become comfortable with the elementary operations that will allow you to find the solutions, if there are any solutions, and also to write down solutions. So let me remind you of what we had. So first of all, we had given a linear system of equations. There are three elementary row operations. Elementary equation operations. So the first one is exchange to equations. So swap the first equation with the third equation, for example. The second is multiply an equation by a non-zero number. So for example, multiply equation 2 by 25. Add a multiple of one equation to another. So for example, you've got equation 3, and you replace equation 3 with equation 3 plus 29 equation 2. So using these elementary equation operations, you can transform one linear system into another linear system. And if you do a bunch of them, then you can transform one linear system into an easily solved linear system. So just a little bit more language. So we say two linear systems are equivalent if you can transform one system into the other using elementary equation operations. So on Monday and on Tuesday, I did this. I started with a complicated linear system. I did elementary equation operations, and I got a simpler linear system. And then I solved the simpler linear system, and I said, well, the solutions of the simpler linear system are solutions of the more complicated linear system. So what I did was I started with a complicated linear system. I did some work. I ended up with an equivalent, easily solved linear system, and I wrote down the solutions of the easily solved linear system. Now, this is all wonderful as long as this process doesn't mess up the solutions. Because a linear system can either have no solutions, exactly one solution, or infinitely many solutions. And if this process messed with that, you start with a complicated system which has no solutions, and you do some stuff, and you end up with an easily solved solution which has exactly one solution, what's the point? The important conceptual step is that this stuff does not mess up the type of solutions. So you have one system So you have one system, which is complicated. And it will have, so it will have one of two things, one of three things. Either it has no solution, or it has exactly one solution, or it will have infinitely many. The point is that if this complicated system is equivalent to a simpler system, then either they both have no solutions, or they both have exactly one solution, and that one solution is the same, or they both have infinitely many solutions, and the infinite set of solutions of this is precisely the infinite set of solutions of that. So that's a theorem. Equivalent linear systems have exactly the same solutions. And I sketched the beginning of the proof of that at the end of class on Tuesday. I'll write it up properly and post a PDF file today or tomorrow. So are there questions about any of this? The big picture is someone gives you a complicated problem, you do a bunch of stuff to it to reduce it to a simpler problem, and the stuff that you did with it did not break the solutions. Questions? Okay, so now I'm going to just introduce shorthand. So you remember from Monday and from Tuesday that when I was doing all of those elementary equation operations, I would first write down a system, and there was an x1 and an x2 and an x3, and then another x1 and another x2 and another x3, and blah, blah, blah. And then I did something, and I had to write another system, and there were a whole bunch of x1, x2, x3s, and then I did something, and then there were another bunch of x1, x2, x3s. And I spent a lot of time writing brackets, and I spent a lot of time writing x1, x2, x3, maybe x4. I spent a lot of time writing brackets and variables, when in fact what really mattered were the numbers in front of the variables. And so what we're going to do is we're going to introduce a shorthand, which is we'll start with a bracket and some variables, but then we will just backburner the bracket and the variables. We'll do the elementary equation operations, and then at the end, we'll put the brackets and variables back in and solve it. So it's just going to be a shorthand. So this is the augmented matrix notation. So we are going to introduce augmented matrices. And all an augmented matrix is it's simply a shorthand. So if you're given a problem, which is find all solutions of the linear system, first equation is x1 plus x2 plus 2x3 plus x4 equals 3. Second equation is x1 plus 2x2 plus 4x3 plus x4 equals 7. Third equation is x1 plus x4 equals minus 21. So you're given this problem. You need to solve this problem. Right now, if I were to start doing elementary equation operations, I would be writing this bracket a whole bunch of times, and I would be writing a whole bunch of x1, x2, x3, x4s as I went through the procedure. So rather than doing that, we simply introduce the augmented matrix. So the augmented matrix is going to have 3 rows because there are 3 equations. The augmented matrix will have 4 columns, 1 for each variable. And then we'll have a 5th column for the unknown, for the right-hand side. So the augmented matrix is going to be a 3 by 5 matrix. The coefficients are going to be on the left, and we're going to keep them in order. And the right-hand side will be the rightmost column. So I'm going to put the right-hand side in, 3, 7, 1. And I put that vertical line there to minus 21. It's tragic. I put that vertical column there to remind myself that this is the right-hand side. Some books, some videos, some instructors do not put that vertical line there. They just let you mentally remember that there's a vertical line, that this column is separate from the other columns. This book and this instructor put a vertical line there. Okay, so this column is going to be the coefficients that are multiplying x1. This column is going to be the coefficients that are multiplying x2. This column is going to be the coefficients that are multiplying x3. And this column is going to be the coefficients multiplying x4. So the coefficients multiplying x1, first equation we have a 1. Second equation we have a 1. Third equation we have a 1. Coefficients multiplying x2, first equation we have a 1. Second equation we have a 2. What's the coefficient multiplying x2 in the third equation? 0. So proceed, 2, 4, 0, 1, 1, 1. Now, you notice when I wrote this equation, I put x4 all the way over on the right-hand side. That was just a matter of good hygiene. I like to write my variables in columns so that I don't mess up this step. So this is the augmented matrix. And we also write it as A line B. I'm busy. Tell them I'm busy. It's okay. So we write this as A, B, where B is the right-hand side, 3, 7, minus 21. And A is the coefficient matrix, 1, 1, 1, 1, 2, 0, 2, 4, 0, 1, 1, 1. This is the coefficient matrix. This is just language. Right now, the phrase augmented matrix and coefficient matrix might or might not be alien, but within 2 lectures, it will be less alien. Okay. So here we had elementary equation operations. Here we will have elementary row operations. So every time we do an elementary equation operation on this system, that would correspond to an elementary row operation on this system. Except that this is much easier and faster to write because I don't have to write all those plus signs. I don't have to write those equal signs. I don't have to write those x1s, x2s, x3s, x4s. So directly analogous to the elementary equation operations are the elementary row operations. So this is just shorthand. So I'm going to start with the augmented system for the original linear system. 1, 1, 1, 1, 2, 0, 2, 4, 0, 1, 1, 1, 3, 7, minus 21. And I'm going to do elementary row operations, which are going to be the analog of the elementary matrix operations. So first, I'm going to keep that x1, and I'm going to use it to knock out x1 from the second equation and from the third equation. So that means I'm going to replace equation 2 with equation 2 minus equation 1. And I'm going to replace equation 3 with equation 3 minus equation 1. In terms of rows, I just write this as row 2 minus row 1, row 3 minus row 1, and then I put a tilde. The tilde means equivalent to. So here, this is just reminding myself what I'm doing. Row 2 minus row 1 goes into row 2. Row 3 minus row 1 goes into row 3. Row 1, nothing's happening, so I immediately copy it over so that I don't have any copy errors, because at this point I'm going to have to think. Row 2 minus row 1. 1 minus 1 is 0. 2 minus 1 is 1. 4 minus 2 is 2. 1 minus 1 is 0. 3 minus 7 is 4. Row 3 minus row 1. 1 minus 1 is 0. 0 minus 1 is minus 1. 0 minus 2 is minus 2. 1 minus 1 is 0. Minus 21. Minus 3 is minus 24. So I have performed 2 elementary equation operations. And now I'm going to do one more. So I'm going to replace equation 3 with equation 3 plus equation 2. In terms of the augmented matrix, I'm going to replace row 3 with row 3 plus row 2. And then I put my tilde. I am only messing with row 3, so I just quickly copy over the rows I'm not doing anything with. 0, 1, 2, 0, 4. 0 plus 0 is 0. Minus 1 plus 1 is 0. Minus 2 plus 2 is 0. 0 plus 0 is 0. Minus 24 plus 4 is minus 20. Now, at this point, I'm going to stop. And I'm going to write the linear system. So I'm stopping, and what I have is that the original system, the original linear system, is equivalent to the linear system. So I need to unpack this into a linear system. These are the coefficients. This is the right-hand side. This column represents x1. This column represents x2. This column represents x3. This column represents x4. So the first equation I get from the first row, I get x1 plus x2 plus 2x3 plus x4 equals 3. From the second row, I get the second equation. x1 plus 2x2 plus 2x3 equals 4. And what equation do I get from the third row? 0 equals minus 20, negative 20. This has no solutions. So the original system had no solutions. Are there questions? All right, so let's do another example. Now, let's say we were given the linear system x1 plus x2 plus 2x3 equals 1, 2x1 plus x2 plus 4x3 equals 3, 3x2 plus 2x3 equals 1. And we're asked to find the solutions. So the first thing I'm going to do is I'm going to write down the augmented matrix. So the augmented matrix is going to have how many rows? Yes.
Can we do the same procedure to the columns also?
There are elementary column operations, but they're not going to help us solve equations. They will come up. They will come up in a few weeks, but not right now. And they will be important, but just not in terms of solving linear systems. Are there other questions? Okay, so the augmented matrix is going to have how many rows? 3, because there are how many equations? 3. The augmented matrix is going to have how many columns? 4, because there are how many unknowns?
3.
And 1 right-hand side. So the augmented matrix is 1, 2, 0, 1, 1, 3, 2, 4, 2, 1, 3, 1. So I'm going to do the elementary row operations one more time, slowly, and then I'm going to ask you to start just trusting me on the final results. So I'm going to take this 1 and knock out that 2. So I'm going to replace row 2 with what? Row 2 minus 2, row 1. And then I put my tilde. Okay, so first I copy over the equations. The rows I'm not doing anything with. So I don't. The moment I start trying to do arithmetic, I start making mistakes. I don't want to make any mistakes yet. Okay, row 2 minus 2, row 1. 2 minus 2 of that is 0. 1 minus 2 of that is minus 1. 4 minus 2 of that is 0. 3 minus 2 of that is 1. Yes?
Why this time you did R2 minus 2 R1?
Because I wanted to use this 1 to kill everything below it. And so to get rid of this 2, I'm going to have to subtract 2 of these. Are there other questions? Okay. Now I'm going to, for reasons you'll see, I like to have 1s whenever possible. So I'm going to replace row 2 with minus row 2. So I just write minus row 2. And I put a tilde. And that leads to the new system, 1, 1, 2, 1, 0, 1, 0, minus 1, 0, 3, 2, 1. Now, I'm going to use, now I have two choices. One choice is I could use this to knock out this 3, and then I would get a system of equations where this equation involves x1, x2, x3. This equation involves x2, x3. If I managed to knock this out, this equation would just involve x3. I could use the third equation to solve for x3, then use the second equation to solve for x2, then use the first equation to solve for x1. So if I wanted to just take it to the point of back substitution, all I would need to do is knock out this 3. But I'm going to take it beyond the level of back substitution because I'm actually more comfortable doing row operations than I am doing back substitution. The moment I start doing back substitution, I'm like writing equations. I've got x1, x2, x3 running around. It's just messy. And so I'm just going to keep going. I'm going to use this 1 to knock this out. And I'm going to use this 1 to knock that out. Because my goal is equation 1 is going to give me information about x1. Equation 2 is going to give me information about x2. And one hopes equation 3 will give me information about x3. So I'm going to use this 1 to knock that and that out. So row 1 is going to be replaced with row 1 minus row 2. And row 3 is going to be replaced with row 3 minus 3 row 2. And then I put my tilde. So first I'm going to just copy over row 2 because it doesn't get, nothing happens to it. Okay. This minus this is 1. This minus this is 0 by construction. This minus this is 2. This minus this is 2. This minus 3 of that is 0. This minus 3 of that is 0 by construction, by choice. That's what I wanted. This minus 3 of that is 2. This minus 3 of that is 4. And hold on. All right. So now I'm going to replace this with a 1. So I'm going to take row 3 and divide it by what? 2. So 1/2 row 3 is equivalent to, so 1, 0, 2, 2, 0, 1, 0, minus 1, 0, 0, 1, 2. And finally, I'm going to use this to knock out everything above it. So I'm going to replace row 1 with row 1 minus 2, row 3. Okay, so row 2 and row 3 just go along for the ride, so I'm just going to copy them over. 0, 0, 1, 2. This minus 2 of that is 0. This minus 2 of that is, whoops. This minus 2 of that is 1. This minus 2 of that is 0. This minus 2 of that is 0 by construction. This minus 2 of that is minus 2. Now I stop. The first equation has to do with x1, and none of the other equations have to do with x1. The second equation has to do with x2, and none of the other equations have to do with x2. The third equation has to do with x3, and none of the other equations have to do with x3. So at this point, I write down the linear system that this is the augmented matrix for. And this is the augmented matrix for the linear system x1 equals minus 2, x2 is equal to minus 1, x3 is equal to 2. Can you check that this is, can you easily solve that? Yes. And now, once you have this, you can plug it into the original system. Let's just check the first equation to see that we haven't completely messed up. So we would have this plus this is minus 3. Plus 2 of that is minus 3 plus 4. So this certainly satisfies the first equation. You would then plug this in. You would then plug the solution into the second and third equation, and find that you have a solution. Yes.
If there's only one solution, could you always reduce it to the identity?
Yes. Yes. So this is the question is, if there's exactly one solution, will you always end up with something this beautiful on the left-hand side? And the answer is yes. Yes.
Do we have to show all of this, or can we just stop there?
Okay, so the next question was, could I have just stopped here? And the answer is, if you were just asked to find all solutions of that linear system, you could have stopped here and then gone to the linear system and then found the solutions. Or you could have just knocked this 3 out and stopped there and found the solutions. If you were asked to find the reduced row echelon form, then you would have to go all the way. But it just depends on what you're being asked. Okay, so let's do another example. So you notice in the end, we ended up with, so let me just introduce some language. These are called leading ones. The augmented matrix has 3 leading ones. There's a leading one in the first column in the first row. There's a leading one in the second column in the second row, and there's a leading one in the third column in the third row. Yes?
Instead of just like all ones for that identity there, what if they're like scalar multiples of the one? Would that work as well?
So it'll work in terms of finding the solution. The thing that's sort of interesting about these problems is everybody in the classroom would start with this matrix. Everybody in the classroom might have their own procedure. And so everybody in the classroom might have a different path here, but everybody in the classroom will end up at the exact same place as long as we demand that these be ones. If we were willing to stop when this is non-zero, then you might have 10, 0, 0, minus 20. The person to your right might have pi, 0, 0, minus 2 pi, and so forth. But if you demand that you go all the way to these being ones, everybody in the classroom will have the exact same final matrix. And so that's why we try to take it always to the end. In Matlab, there's a command that will do this. Wolfram Alpha, there's a command that will do this. And I should tell you what that command is. So if you wanted to double check your work and you're doing Matlab, what you would do is you would just say S is the matrix 1, 1, 2, 1, semicolon 2, 1, 4, 3, semicolon 0, 3, 2, 1, bracket. You define the matrix. Then at the command line, you would say RREF of S, and Matlab would give you this. So if you're ever wanting to check your work, that's how you would check your work with Matlab. If you're in Wolfram Alpha, what you would ask for is, and Wolfram Alpha obviously you have wherever you have a browser. If you were in Wolfram Alpha, you would just type RREF of curly bracket, 1, 1, 2, 1, curly bracket, 2, 1, 4, 3, curly bracket, 0, 3, 2, 1, curly bracket. So that's, if you did this into Wolfram Alpha, the first thing it would do is it would say, I think you're asking for the reduced row echelon form of this matrix, and you would look at it to make sure you hadn't made any mistakes. The second thing it would do is it would give you this. So whenever you're trying to double check your work, MATLAB, Wolfram Alpha, Maxima, Maple, whatever, there's this thing called reduced row echelon form, and that is what everybody will end up at as long as you demand that the first non-zero entry be a 1, as long as you demand that all the 0 rows are in the bottom, if there are any, as long as you demand that above any leading 1, above and below any leading 1, there are zeros, and so forth. So we can talk about that shortly. I want to do some more examples, though. Are there questions? Okay. Okay, so let's imagine you were asked to find all solutions of x1 plus 2x2 minus 3x3 equals minus 5, 2x1 plus 4x2 minus 6x3 plus x4 equals minus 8, 6x1 plus 13x2 minus 17x3 plus 4x4 equals minus 21. 3 equations, 4 unknowns. Gesundheit. So the first thing you would do is you would write down the augmented matrix. So the augmented matrix is going to have how many rows? 3. How many columns? 5. So I put in the column for the first unknown, 1, 2, 6. Second unknown, 2, 4, 13. Third unknown, -3, -6, -17. Fourth unknown, 0, 1, 4. Right-hand side, -5, -8, -21. And now, in the privacy of my own office, I do a bunch of elementary row operations. And I end up with the following equivalent matrix. 1, 0, -5, 0, -7. 0, 1, 1, 0, 1. 0, 0, 0, 1, 2. So I have a leading one here, a leading one here, a leading one here. Above and below each leading one, I have zeros. Above and below this leading one, I have zeros. Above and below this leading one, I have zeros. These are ones. If I had any rows that were just straight up 0, they would be at the bottom. This is the reduced row echelon form of this matrix. Now, once you get to the reduced row echelon form, the good news is that you can check with your roommate whether or not your roommate also got the same reduced row echelon form. You can check with Wolfram Alpha. You can check with Matlab. You can check whether or not you made any mistakes at this point. So getting from here to here takes about 4 minutes, and I'm not going to do it. Once we're at this point, we write down the equivalent, we write down the linear system for that augmented matrix. So our original linear system is equivalent to the linear system x1 minus 5x3 equals -7. x2 plus x3 equals 1. x4 equals 2. So at this point in the game, all of the solutions of this are precisely the solutions of the original thing, because we did elementary equation operations, which were, in shorthand, elementary row operations. Do you know for sure what x4 equals? Yes. On the other hand, here you have 2 equations and 3 unknowns, x1, x2, x3. So for sure you know x4 is 2, but you don't know what x1, x2, and x3 are. So you're not going to have, at this point you know immediately there will be infinitely many solutions. At this point you know that. So now I'm going to write down the infinitely many solutions. So first of all, I know for sure that x4 is equal to what? 2. Now x3, I don't know what it is, but if I told you that x3 was 10, you could use equation 2 to tell me what x2 is. And similarly, you could use equation 1 to tell me what x1 is. So equation 2 will determine x2 in terms of x3, and equation 1 will determine x1 in terms of x3. So x3, we don't know. On the other hand, x2, we know for sure is 1 minus x3. And x1, we know for sure is minus 7 plus 5x3. So whatever value x3 takes, that will then determine x1 and x2. So we say that x3 is free. x3 can be whatever it wants to be. It will then determine x2 and x1. So we would write the general solution is x1 equals minus 7 plus 5t. x2 is equal to 1 minus t. x3 is equal to t. x4 is equal to 2. And t can be any real number. The reason this represents infinitely many solutions is because t can be any real number. Each person in the class could choose a different value of t. Each person in the class would get a different specific solution. This is the general solution because all solutions are of this form. So now, let's just actually check that this puppy is a solution, because I make mistakes. So what we're going to do, should I plug this into that system? Or should I plug it into the original system? Original system. We're pretty sure we haven't made a mistake going from the reduced system to our solutions. We want to check it for the original system. So we're going to take that and we're going to plug it into the original system. So the original system was x1 plus 2x2 minus 3x3 equals minus 5. 2x1 plus 4x2 minus 6x3 plus x4 equals minus 8. 6x1 plus 13x2 minus 17x3 plus 4x4 equals minus 21. And we want to see if we plug this thing in, which just depends on t, whether we satisfy all three of these equations. So I'm going to plug my general solution in to my linear system. So the first equation is x1. Well, that's minus 7 plus 5t. Then I have plus 2 times x2. Well, that's 1 minus t. Then I have minus 3 times x3. Well, that's t. And I want to know if that equals minus 5. My second equation is 2 times x1, so that's 2 times minus 7 plus 5t, plus 4 times x2. x2 is 1 minus t, minus 6 times x3, well, x3 is t, plus x4, well, x4 is 2. And I want to know if that equals minus 8. And now my third equation is 6 times x1, well, that's minus 7 plus 5t. Plus 13 times x2. x2 is 1 minus t. Minus 17 times x3. Well, x3 is t. Plus 4 times x4. x4 is 2. And I want to know if that equals minus 21. Are people clear on what I am trying to do? OK. So now I'm going to just massage that. So the first equation, what I'm going to do is I'm going to separate the constants from the t's on the left-hand side. So on the first equation, I have minus 7 plus 2 plus t times 5 minus 2 minus 3. And I want to know if that equals minus 5. So I separated the constants from the t's on the left-hand side. On the second equation, I have minus 14 plus 4 plus 2 plus t times 10 minus 4 minus 6. And I want to know if that equals minus 8. Third equation, I have minus 42 plus 13 plus 8 plus t times 30 minus 13 minus 17. And I want to know if that equals minus 21. Are people okay? All right, now, on a moral level, t can be anything. So that left-hand side, that t could be anything. Are there any t's on the right-hand side? No. So you are going to really, 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 really hope that this adds up to what? 0. Because if it adds up to 1, then on the left-hand side you have something plus t equals minus 5. Is that going to be true for all t? If this does not add up to 0, I'm going to have something plus 28 times t equals minus 5. Will that be true for all t? No. So you really, really hope that adds up to 0. And you really, really hope that adds up to 0. And you really, really hope that adds up to 0. Does it? Yes, that's because we had the correct numbers multiplying t. Minus 7 plus 2 is minus 5. Minus 14 plus 4 is minus 10. Plus 2 is minus 8. Minus 42 plus 13 is minus 29. Plus 8 is minus 21. So this is true for all t in the real numbers. We really do have a solution. We really did solve the original system. All right. Now, somebody could equally well say, once we were at this point in the game, what I said was x2 is determined from x3, x1 is determined from x3. But a cautious student could say, well, why did you pick on x3? Why didn't you say, well, let's solve for x3 in terms of x1, and then this is going to be an equation in x1 and x2, and then we'll solve for x2 in terms of x1. And x1 will be our free parameter. So let's finish by doing that exercise. And I will convince you, that will, I hope, convince you that you don't want to do it ever again. Because you saw how easy it was here. Because x3, that had to do with the structure of that system. But let's not be so clever. Let's say that we will use equation 2 to solve for x2 in terms, x3 in terms of x2. So I'm going to say that x3 is equal to minus x2 plus 1. I'm going to have x2 as my free parameter. Use equation 1 to solve for x1 in terms of x2. So equation 1 tells us that x1 is equal to 5x3 minus 7 is equal to 5 times, well, x3 is minus x2 plus 1 minus 7 is equal to 5x2 plus 5 minus 7 is minus 2. And so if I had decided to write everything in terms of x2, I can. And I get the general solution. The general solution is x1 is something, x2 is t, x3 is something, x4 is 2. x1 is minus 2 minus, I'm just so positive, minus 5t. x3 is 1 minus t. Or I could have solved, I could have solved for everything in terms of x1. And after some work, I would have gotten the general solution. x1 is t, x2 is minus 2/5 minus t times 1/5. x3 is 7/5 plus 1/5 t. x4 is 2. This is a totally general solution. This is a completely correct answer. This is a completely correct answer. But doing it this way and doing it this way take more work. That's why we didn't do it that way. So you need to go through this on your own and convince yourself that for this problem, solving in terms of x3 was the smart thing to do.